You should probably not date your notes like I did. I put the different dates on there, so in case you were absent, I'll really know where the writing line was, or in case you travel. Mr. Chester went over some important things yesterday that you really would need to know and make your project much easier to do. Remember, I use symbols. You should use symbols in your notes, and the goal is that you're putting notes in your own language, not necessarily in, make it student friendly. You don't want to be using lots of large vocabulary for your notes. You should not waste time correcting your spelling when you take notes. The next time you open it, then just run a spell check. With taking the notes, you want to focus on getting all of the right information recorded down. So don't worry about making misspellings. You can fix that later. Try and use symbols so that you can type a little faster to put the information in. And don't make them chronological. Make them be by topic. So if we cover something today in lecture that really relates to the mass of an object, you don't want to start a new box. You want to go back up to where it's talking about the mass of an object and put it in at that point. So we're going to be looking at electric motors and more on the electric and magnetic forces.
But I really know what all about.
I think we left off on electromagnetic. This is
Sound like a dog.
what a magnetic field looks like. Okay, and you can test this by taking what's called a bar magnet. That's just a magnet that's in a long straight line, and getting a bunch of iron filings, which is just basically iron dust. Okay, put the bar magnet in it, and it will generate this pattern in the iron filings. They will align themselves in this way. Okay, and this is the way the field, the magnetic field, works. Okay? And if you play around, it's hard to see with an iron filing. It's easier to see with a paper clip or something. Even objects like paper clips, when you hold a magnet close to them, that basically creates a magnetic field inside the paper clip. So now the paper clip has a north and south pole. And if you get close to it, once the magnetic field is in it, you'll see the paper clip flip and move depending on which pole of the magnet you're holding towards it. So if you flip your magnet around, then the paper clip will flip around. Okay? So you can mess around with stuff like this. Now, I want you to look at that field. When electricity is flowing through a wire, it creates a magnetic field around the wire. Okay? And if you wrap the wire in a coil, you increase the strength of that magnetic field. Here's the field going around the wire. If you loop it, it's the same field, it's that same loops, okay? But they align themselves with the coil, and it amplifies the field. Now I want you to look at the electromagnetic field, magnetic field. See any similarities there?
Yeah.
It's the same thing, right? This is the same force. If you wrap it around a material that's typically magnetic, like iron or cobalt or nickel, then it induces a magnetic field in the iron and makes the whole thing even stronger. To induce means to create within. Okay? So if you wrap it around what's normally a magnetic material, like iron, it creates an even stronger magnet. Okay? And so you can build an electromagnet like this. That's a nail, some wire. The wire needs to have an insulating coat on it. It can't just be a bare metal wire. Okay? You need to get wire. You can build an electromagnet for $3. Okay? Especially if you have a battery. You probably have enough stuff around the house if you have a battery lying around. Depends on if you have wire and nails, but like at my house, I can build a bunch of these real quickly. And you can experiment with them and see if, hey, if the wire's straight, it's a weak field. If I make one loop, it becomes a little stronger. What happens if I make 2 loops, 3 loops, 4 loops? What happens if I put those loops around a nail? And you can experiment with that. And that could be something potentially you could use for the project. In fact, it lists it. We'll talk about it in a minute. Okay, now what good is all this electromagnet stuff? I showed this yesterday before we left, right? If you put a current, this is a wire, okay? This is a wire. This is a battery. If we hook it all up, electrons will flow through the wire. The wire is in a loop. I mean, forget about the square corners. It's going around, so that it's creating a coil, okay? What is that wire now? It is a conductor, but what have I made if I wrap the wire in a loop and run a current through it? Can you flip back to this red one right here? Right there is what I'm pointing at. There it is. Put the wire in a loop and I get a what? You get an electromagnet. Now go back to this blue one here. I put the wire in a loop and I get what? An electromagnet. The electromagnet has a north and a south pole, just like a regular magnet. If the north pole of the magnet is here and it's up against the north pole of a regular magnet, what do you predict will happen?
Repel.
It'll repel. If the south pole of the electric field is near the south pole of a magnet, what do you predict will happen?
Repel.
Which means that if this thing is mounted on some kind of thing that rotates, then it'll do what?
It'll create a mill, a windmill.
A windmill?
Well, an electrical, well, a magnet, I guess.
A magnet mill. We more commonly call this thing that when we put electricity into it, it spins around real fast. A motor, an electric motor. This is how an electric motor works. By running it, I mean, it does work like a mill, except that it's using a different type of energy to drive it. Okay, it's using electricity instead of wind. So we pump electricity through, okay, and the magnetic fields repel each other, and it causes it to turn around. Now they have it set up. There's a split in between here, so it stops. There it stops sending electricity, and now it sends electricity the other way. There it stops, and now it sends it the other way, okay? So it's reversing the field back and forth so that it will continue to always match up south to south and north to north. And by putting electricity through this coil, you can make it turn around. And if it's powerful enough, you can make it turn a wheel to drive a car, or you can make it turn, you know, a grinding mill or whatever. You can hook that motor to whatever you want. Now let me ask you this, given what you knew about electromagnets, what would happen if I added extra loops of wire before I came back to the battery, do you
Wouldn't
think?
it go faster?
Why?
Because the current's stronger.
Not the current's the same, but you're close, you're really close. There's the same amount of current, but by adding more loops,
Field's stronger.
it makes the field stronger. And so it means that the motor spins faster, okay, or with more power. Now, here's the thing most people don't know. Not only is that an electric motor, it's also an electric generator. An electric motor and an electric generator are exactly the same thing. If you put electricity in, it will cause the motor to spin. If you put a crank on the shaft so you can turn the motor, it'll spit out electricity. This is how generators work. it's the same thing. If you want it to generate, you put in motion, and it generates electricity. If you want it to spin, you put in electricity, and it generates motion. And the reason is that as you crank it, if you put a crank on there, as it passes through these magnetic fields, it forces electrons to flow around in a circle. And that's what electricity is. Electrons moving through something. Okay? So a generator and a motor, electric motor, are the same thing. Okay? You can look this up. You can build one of these little motors pretty easily. It's a little harder than the electromagnet, but you can do it. It's real easy to do if you use a cork in a glass of water, because you can let the cork spin around in the water, and that's technically a little tiny electric motor. You get a magnet. So it's a few more components than building an electromagnet. You don't have to have a permanent magnet, but it's possible to do. Okay? It's not that hard. If you look it up, you can find ways to do it. And if you were to do that, you could use it for what? Project. You don't even have to build it. If you find an old electric motor, you can demonstrate these properties. Okay? There are lots of, are there still like those Tonka trucks? You used to have those little Tonka trucks you put a AA battery in and it would drive around. Those have little electric motors in them. You can order electric motors on eBay for, 10 of them for $1 or something. You get them pretty cheaply. Well, there's that. So you can build one. You don't have to build anything. You could draw it out and describe it well enough. You don't have to spend any money, you don't have to build anything to do these projects. You have to show us in some way, through some kind of experiment. It can be a thought experiment if you make it really clear that you understand the principles. Okay. Real quickly, and there's a motor spinning. So, let's see. Okay, I was going to show you something called the left-hand rule, and I can just show it to you. I will get these links and post them at some point. How what?
How does it run?
Well, it doesn't run anything. You would have to hook it up to something. This is just a demonstration motor. Remember, somebody had to invent this. So scientists working on stuff figured out that, oh, here's this weird thing that happens, and then some inventor said, hey, I wonder if I could make that do some work of some kind to replace a windmill or a water mill or something. And then eventually somebody got one to work, and then somebody got one to work well enough that they could attach it to something and actually make it do work for them. And today, things like electric cars, this is what they use, a very sophisticated version of this. An electric table saw.
The chainsaw.
Chainsaw doesn't use this. An electric chainsaw does, but like my chainsaw uses gasoline, okay? So they're not electric. Say what?
That's a whole different process.
That's a whole different thing. But if you're going to use electricity to drive a motor, this is the basics of how it works. So the left-hand rule is this. Take your hand and do this with it. Take your left hand and do this with it. Or this first finger pointing this way, second finger pointing this way, thumb pointing up. Okay? This is called the left-hand rule. You're not going to have to know this yet. You're not going to have to know this for the project, but I want you to know it because it's just a general rule of thumb. Okay? If you take this finger and align it with the direction of current, okay, so that way, and this finger and align it with the direction of the magnetic field, so this way, then your thumb will point in the direction that this thing is going to get pushed. Okay? So that tells you that this is going to get pushed up. Now, to do it the other way, you have to flip your hand upside down, okay? Right. So finger in the alignment of the direction of the magnetic field. This finger aligned with this arrow, and your thumb tells you that this is going to get pushed down. So when you apply current, it tells you that this motor is going to spin this direction. Okay? It's called Fleming, I think it's Fleming's left-hand rule. Okay? It's just a handy thing if you're trying to figure out. My brother, the physicist, used to work at Baldor Electric in Fort Smith. They made electric motors. He worked in their research lab. And so he used this all the time when he was designing an electric motor to figure stuff out. Okay? Left-hand rule. Okay, now, real quickly, before we let you go, let's talk about what does this matter to you? Okay? Well, here are your tasks. Ask questions about data to determine the factors that affect the strength of electric and magnetic forces. The important part of the sentence is, hey, what affects the strength of electric and magnetic forces? Oh, there's one other thing I need to show you. Yeah, one other thing I should show you. Here's a thing that affects the strength of forces, and its distance. And this is a basic rule that works for any kind of force that starts at a central location, or light, okay, a flashlight. This is a rule. It's called the inverse square law. And it says that if I go a certain distance away from, like, let's say a flashlight, the light bulb itself, where the light's coming from, if I go a certain distance and I measure the light's intensity, okay, if I go double that distance, the light will be how much weaker? You think half, right?
Yeah.
But it's not, it's 1/4. It's called the inverse square law because it's 1 over whatever your distance is times itself. Okay, or sorry, squared. So if I go 3 times as far away, it's 1/9. If I go 4 times away, it's 1/16. Say it louder. If I go 5 times away, it's 1/25.
Oh.
If I go 6 times away, it's 6 times 6. 36. Okay? And that works the opposite direction. If I'm this far away, the force is 1/4 as strong. If I go half the distance, it is now 4 times stronger than it used to be. That's why the electrons in my fingers and the electrons in this table, they are pushing, they will tend to resist each other. They're really far apart right now. As I get closer and closer, you can't feel it because the force is really weak, okay? Until you get really close, and then all of a sudden, as you get closer, 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 it's really strong, and that's why you can't actually get those electrons to touch each other. Because the force just goes way up the closer you get. Okay? The same thing works with magnets, both in terms of pulling things and pushing things. So if 2 magnet north poles, the closer they get, the stronger they'll push each other apart. Or north and south, the closer they get, the stronger they'll pull each other. The same thing works with gravity. Okay? If you have a giant, massive object, like the planet Earth, the closer you get to it, the stronger the gravity gets, and it follows the same rule. Okay? If you're 10 miles away and gravity is one unit, when you get to 5 miles away, it's 4 times stronger than it used to be. Okay? So when you're 4 miles away, when you're 5 miles away, whatever that strength is, when you get to 2 miles away, it's now 4 times stronger than it was. So the closer you get, the stronger it gets. That's a basic rule about the strength of these forces. And it's a basic rule about how strong light will be, for example. So, how do we use this to do our project? What affects the strength of electric and magnetic forces? And then here it says, you could use examples of devices that use electric and magnetic forces. Could include electromagnets, electric motors, or generators. Now let me ask you something. Does an electric motor have an electromagnet inside of it? Yes, it does, on a wrench. Does a generator have an electromagnet inside of it? Yes, it does, because an electric motor and a generator are the same thing. You can build any of these things, and look, examples of data that would show you what affects the strength. Examples of data could include the the number or strength of magnets on the speed of an electric motor. If I add more magnets, does it speed up? It could include the number of turns of wire in your electric motor. It could include the number of turns of wire on the strength of an electromagnet. Hey, as I increase the number of coils, does the electromagnet get stronger? You should find a way if you could test that. Okay? Next one. Construct and present arguments using evidence to support the claim that gravitational interactions are attractive, that gravity pulls, it doesn't push, and that strength of the gravity depends on the mass of the interacting objects. The more mass there is, and the closer together that the particles of that mass are, the stronger gravity it has. Okay? And if you get enough things really close together, the gravity can get so strong that light cannot escape. And we call that a what?
Black hole.
A black hole. That's what a black hole is. In the middle of a black hole is probably a supermassive giant star. Okay? You can't see it because the light from that star can't get to your eye because it's caught by the gravitational field of the black hole. But there's a certain point called the event horizon that if you crossed over the event horizon, all of a sudden you'd be able to see the light. Because you'd be in there with it. Now, you'd never be able to escape. You'd be stuck there. But you'd be able to see that star then, theoretically. This one, you're not going to be able to play around with the planets, right? So, examples of evidence for arguments could include data, okay, stuff you find out, generated from simulations or digital tools, and charts displaying mass. So in this one, you don't even have to do an experiment. You just have to look up some stuff on, hey, how does mass, as mass increases, how does it affect gravity? Okay? You can find videos that show this. You can find simulations. There's lots of cool simulations you can do online that you can use to show this. Last one. Conduct an investigation and evaluate the experimental design to provide evidence that fields exist between objects exerting forces on each other even though the objects are not in contact. Now, it's hard to show that my hand is not in contact with the table. And really, we consider this to be in contact. It's close enough. Even though technically you now know they're not really touching. So it's hard to show this one. It's possible that you could show it. I can think of ways that maybe you could show it. But other things, can you think of other forces that affect an object even though they're not touching? Has anybody ever used the little magnadoodle thing where you put the beard and hair on the guy?
Yes.
Yeah.
Are you touching the aluminum filings inside there with the magnet? The magnet's not touching it, but the field is touching it from a distance. You could do an experiment, potentially, using a magnadoodle to show this. If you built an electromagnet to do the first one, you could use the electromagnet to show this one as a separate thing. Does everybody get the idea? Okay, any questions? So we're going to let you have work time from here on. Okay, you may ask us, she's going to show you some notes, and then you may ask us questions if you have questions about how you want to do your unit run.
So some folks are still getting down from yesterday's lecture. So there, in case you were a little bit slow on getting that down. And then what we cover today is very short. Again, don't worry about spelling the words right. More important is you get the content down. And we will come around and discuss with you what you're going to do with your Unit 2 project.
And I
guess theoretically you could discuss if you're having problems with your unit run project, right?
If you're, whatever you are having issues with.